Hi, and welcome back. So let's continue where we left off last video, where we discussed about the null and alternative hypothesis, and let's talk about test statistics. Specifically, we'll go over what a z-statistics is and how to calculate z-scores. In this second video, we'll talk about test statistics. So let's continue where we left off last session and use the example concerning the body weight. So if you remember, our null hypothesis states that there is no difference in the mean body weight of men ages 25 to 35 between 1990 and now. For now, let us accept the notion that the null hypothesis is true and assume that the current population mean is 170. And we are also aware that the repeated SRS of our sample size taken from this population will yield us different sample means. So this sample size, n, will be 64 for this case. SRS here stands for simple random sample, which essentially is we're choosing a subset of individuals randomly from a larger population set. To make better sense of this, let's have this rectangle here represent the population of men that we're trying to sample from. And in our first SRS with a sample size of 64, we're simply randomly choosing men within this, this set, and then calculating the mean from it. So the simple random sample is chosen in such a way that every set of individuals has an equal chance to be in the selected sample. So a sample 1 with a n of 64 will yield us a sample mean of 173, and then sample 2 yields us a mean of 185, and sample 3 yields us a mean of 164. And if we continue down the sampling methods, we'll eventually come to a distribution of mean that looks normal. So it looks like this, where most of our sample means are now, landing within this 165, 170, and 175 pounds range. And the model here is based, remember, it's based on taking all the possible sample of n equals 64 from a population with a sample population mean of 170 and a standard deviation of 40. The key thing here is even though the population mean is 170, the sample mean themselves differ. The question then becomes, at what point will the sample mean be sufficiently different from 170 to suspect that the claim about the null hypothesis being 170 is false? So if we inspect the sampling distribution of the sample mean further, this should give us some clues about how to answer this question. So based on what we know with our sampling distribution, we can calculate something called the standard error of the sample mean by simply taking the standard deviation and dividing that by the square root of the sample size. So there will be 40 divided by the square root of 64, and if we just plug that in our calculator, we'll get 5. Calculating this standard error will give us the accuracy of the sample mean by measuring its sample-to-sample variability. To put a little bit more simply, the standard error of the sample mean is an estimate of how far the sample mean is likely to be from the population mean, whereas the standard deviation, right, the standard deviation of the sample is the degree to which individuals within the sample differ from the sample mean. So now we can use this info to look at some specific example. Say let's look at 173 and 185 sample means here. So with the sample mean of 173, that's fairly close to 170, right? And based on our null hypothesis, that doesn't provide good evidence against it, which, if you remember, it says that there is no difference in the mean body weight of men ages 25 to 35 between 1990 and now. In contrast, the sample mean of 185 is fairly far away out here in this far right tail. So the sample mean of 185 is unlikely to have come from the sampling distribution and therefore does provide good evidence against the null hypothesis. But the question then becomes, how likely, probability-wise, how likely are we to sample all the way from this tail end where it does provide good evidence against the null hypothesis? To look at this a little bit further, the statistical distance of the sample mean from the hypothesized value of the population mean, 170, provides the weight of evidence against a null hypothesis. And this statistical distance is represented in the form of the test statistics called z-stats, given by this equation here, where x bar is the sample mean and mu naught here is the mean from the hypothesized value of the population mean, which is the 170 here, right? And then the standard error is what we calculated earlier, which is 5. Essentially, a large value of z-stat represents large statistics distance and good evidence against the null hypothesis, and having a small value of z-stats represents small statistical distances and thus weak evidence against the null hypothesis. Let's look at an example where we calculate the z-stats to understand this a little bit better. So going off with our body weight of 25 to 35-year-old men scenario, we had established the test that the null hypothesis is represented as mu equals 170 versus the alternative hypothesis that mu is greater than 170. And all of this is within the population of standard deviation of 40 pounds. And our simple random sample, which our sample size is n equals 64, is associated with a standard error of 5. So with this info, we can ask what is the z-stat score for a sample in which the mean is 173. So we plug into that equation and we get 0.6. So let's compare that to a sample of 185 to see, to compare what that means, right? So with a sample mean of 185, we get a z-score of 3.0. So what does this mean? Since the distribution of z-stat is normal, we can apply what's called the 65, 95, 99.7 rule here in establishing the probabilities. For example, we know that 95% of z-statistics fall between the -2 and 2 standard deviation away. And if you don't know about this rule, the normal distribution is commonly associated with this, which you can see from this image here. It's if we start from the top, it's saying that 68% of the data is within 1 standard deviation of the mean, and then 95% of the data is within 2 standard deviation of mean, and lastly 99.7% of the data is within 3 standard deviation of the mean. So to understand where these percentages come from is out of the scope for this session, but maybe in the future we can make a video on this specific topic. If you would like to learn more about the underlying math and how it works though, I encourage you just to Google probability density function, which is essentially used in this case to specify the probability of the random variable falling within a particular range of value, as opposed to taking on any one particular value. So going back to an example, z-stats that are less than -2 and greater than 2 would be unlikely to come from this distribution, thus casting a doubt on the null hypothesis. Therefore, the probability of sampling a sample mean of 185 that comes from this distribution is sort of unlikely. So how do we calculate this probability score? Well, that's what we'll talk about in our next video, where we will talk about p-value in which we convert our z-score into. Thank you.